Hello, this is Liz Schlemer, and this is a video for IME 315, Financial Decision Making for Engineers. We're going to be talking about Excel functions. So in the 5 categories of topics that we're covering in this class, these Excel functions are most often used in the investment analysis part, and also in personal finance decisions. So I'm going to talk about these sort of 6 functions. Actually, one is an equation, but when we look at engineering economy kinds of topics, we often refer to a timeline, which is called a cash flow diagram, there in green. And so I'm going to be talking about how we use these functions and represent them in that cash flow diagram. So the first one I'm going to talk about is the payment function. And the format of the payment function is you type the words PMT, and then the first input is rate, then end periods, PV, future value, and type. So rate is the interest rate per period. One of the most important things that you need to do in solving engineering economy problems is to define the period. Oftentimes we're looking at a year in engineering investment analysis, but usually we think about a month when we're talking about personal financial decisions. So just remember, the first thing you need to do is what is the period, and then everything else is based on that definition. So interest rate is, if you're doing it a monthly, it's going to be interest rate per month. If you're doing it yearly, it'll be interest rate per year. Number of periods, again, the definition of periods is important here. Is it number of years or is it number of months? The present value, if you remember in the cash flow diagram, that is an amount that's occurring at time period 0. So this particular function is really used for developing the payments on a loan. So the present value is the amount you're getting at time period 0 or the loan amount that you're getting. Future value is, you can also include a payment that accumulates into a future value. If you do that, you usually don't have a present value. But it's also in the function there, when it has brackets around items, those particular inputs are not necessary for the function. But if you're going to put it there, you can put it separated by commas. And then the next is type, where you define when the payments occur, if it's at the beginning of the period or the end of the period. So this is an example. What are the monthly payments on a $5,000 balance in a credit card that has 20% interest if you want to pay it off in 2 years? So remember the thing I said before, it's very important to define a period. In this case, I'm defining it month because I want to know the monthly payments. I don't want to know the yearly payments. I want to know the monthly payments. So that's my definition of a period. So then the rate is 22% divided by 12, or the interest rate per month. The number of periods is 2 years divided by 12 months in a year. And then the present value is 5,000. So I just go ahead and put those values into this function. And you can see, and this is what it looks like when I'm looking at it in a cash flow diagram, the particular loan payment amount. The loan is $5,000, and then I want to know what the payments are over 24 months at 1.83% per month. So I put this in Excel. You can see that's the way I put the function in, and it's okay to do calculations within the input, and I get $259. So that means if I want to pay off $5,000 balance in a credit card that has 22% interest, and I want to pay it off in 2 years, I need to pay about $260 a month. Remember that it looks funny here that number is negative, but the way that they define these functions is it's going to be opposite of the loan amount. So if I put in a negative 5,000 instead of a positive 5,000, I would have gotten a positive 259. So just know that we're trying to balance that equation and just keep it in mind. That's why it's negative. If you remember in accounting, having parentheses around a number indicates that it's negative. Also, the color red indicates that it's negative. So if it was formatted differently, it might say minus 259. But because it's formatted like an accounting number, it has parentheses and in red. So let's look at the next one, which is present value. So it's very, very similar. The rate, the number of periods, the payment amount now, right? Because we're trying to find the present value of a particular payment or the future amount. So if we have the same thing, we have to define a period is very important. So it's interest rate per period, number of periods, equal payments per period. So one of the things that's really important in this particular function is the payment number needs to be equal in all periods. Now, sometimes that's not true. Actually, most of the time that's not true unless you're doing an amortized loan. Future value, so some value into the future, what's the present value of that? And then again, the type, where it's defaults to end of period, but you could also put a 1 in there and it'll be beginning of period. So I want to buy a new car and I need to know how much I can borrow if I want to pay $500 a month for 4 years. So again, we need to define the period because I want to know $500 per month. That defines the period definition. The rate is 6% divided by 12, so it's 6% per year, but we want to do it per month. And then the number of periods is 4 times 12. The payment is $500 because that's what the problem says. And I have this, format of the function is here. So I put in 0.06 divided by 12, 4 times 12, and 500. And you can see what I'm doing here is I'm saying I have 48 months and 0.5% a month. And that gives me $21,290. That's the loan amount that I can get if I want to pay $500 a month. So that on top of my on top of the down payment will tell me how much I can afford if I want to purchase a car. The next one is future value. So in this case, again, it's very similar: rate, number of periods, payment, and again, that has to be equal payments per period, present value, and type. So looking if you could also include an initial number. And then the type, again, is end of period or beginning period. So how much will I have in the bank if I deposit $3,000 on December 31st each year for 10 years? I expect to earn 15% interest. So again, now we've changed the definition of period because I put in the payments, or I put in the deposits into the bank once a year on December 31st. So I've changed the definition of a period. It's now 1 year. So my interest rate is interest per year of 15%. The number of periods is 10 years. $3,000. Oh, that should say $3,000 per year, not per month. Please correct that. And then I put that value into the equation. So I want to know what the future value is if I'm paying $3,000 per year for 10 years. And I put that in there and it comes up with $61,000 at the end of 10 years if I put $3,000 a month, $3,000 a year. The next one is internal rate of return. And we're going to talk about this a little bit further in more detail, these next two, especially internal rate of return and net present value, when we talk about valuation. But it also relates to some of the simpler questions that we are asking. So IRR has two inputs. One is an array of numbers, so a range in Excel, and then an estimate of return. But that particular one is not necessary. Most people just do the range of values and figure out what the internal rate of return is. What this is giving you is an interest rate. So you remember on all the other ones we've looked at so far, we are given an interest rate. But in this one, we're saying, can I find what the interest rate is given a particular set of cash flows? So if I purchase a GM stock in July of 2015 for $29 a share, I received $1.50 of years of dividends, and I just sold it in 2019 for $39 a share. What return did I receive on this investment? So what you're saying is you have these cash flows, an initial investment, returns over time, and then a selling value at the end. And what I'm trying to find is what is that interest rate? So I'm going to go ahead. I have this range of cash flows, 2015 to 2019, the initial investment of $29, the $1.50 each year for 3 years, and then the $39 at the end. And you can see I use the function IRR, and I put that range C3 through C7, and I got 11% return. So what this tells me is that I'm getting 11.36% on this investment. That's my rate of return on the investment. So the net present value is another one that's often used for valuation techniques. And that has a rate that you're using and then an array of numbers. So we'll go ahead and look at that. My friend has offered me the opportunity to invest in a startup. He estimates the cash flow will be as follows. So I have to initially invest $5,000, and then I get returns of $1,000, $2,000, $3,000. If I can earn 4% in my savings account, is this a good investment? So one of the things you need to remember about net present value is that it brings it to the beginning of the period in which you start the array. And that is problematic in the sort of traditional definition of net present value. So you need to adjust this a little bit. And I'm going to talk about this later. But what I have to do here is, you can see I have the net present value, and the C1 is the interest rate. Oh gosh, I have 5% and it should be 4%. There's a mismatch there. I'm going to leave it, but just note that. So the interest rate of 5%, and then the range, I have C4 through C6. So it's really only the year 1, 2, and 3 for the net present value, because that brings it back to the beginning of time period 1, which is the same as the end of time period 0. So then I add to that the investment amount. So I don't include that investment amount in the net present value calculation. But this gives me a 358 positive value. Now, when we talk about evaluation techniques, this will become more clear about why that's important. But let's look at the comparison if I have a bank account. So in this case, I have 5%, not 4%, but I put $5,000, and then I get interest back of $250 in year 1, in year 2, and then year 3, plus I take out the $5,000. So you can see that equation is the same as before. In my spreadsheet, I moved this down a little bit, so that's why it's on C10 and not C2 like the other one. But it gives me 0. So what I can do is I can look at these two returns, and because I've brought everything to time period 0, I can now choose the largest one. So $358 is higher than 0, so this is a better investment. So the question about this particular problem is this a good investment? Is this better than putting my money in the bank? And the answer is yes, it's better than putting your money in the bank. So the last thing I'm going to look at is just the actual equation. If you remember in engineering economy, the future value is equal to the present value times 1 plus I to the n. So you can also use that. So in this case, I have present value of $20,000, an interest rate of 10%, 9 years, and that gives me a future value by using this particular equation. Lots of times I use this equation just because it's as easy to do as the functions. And for a long time, I didn't particularly trust the functions, but in this case, the functions are much better now in Excel, and it's very much trustworthy. But you could also do this equation whenever you're doing engineering economy, trying to shift values from one year to the other. So in this case, I'm shifting $2,000 from time period 0 to time period 9, and I'm earning 10%. So remember, that's like if I put $20,000 in the bank, earn 10% for 9 years, how much money would I have? So I hope that makes sense to you, those overview of Excel, both used in investment analysis and personal decisions.